We present differentiable interreflection-aware physics-based inverse rendering. Given multi-view RGB images of a scene, we present an inverse rendering model that simultaneously estimates illumination, geometry, and materials of the scene. Our framework includes 3 modules. Given the camera parameters of a scene, we first sample rays, and locate surface points hit by the rays by a main tracing module. We then estimate the illumination of the scene by a novel interreflection-aware illumination module, and the materials by a material autoencoder. Given estimated illumination, geometry, and materials, we can render the scene for any given view. By comparing the rendering with the ground truth image, the proposed framework can be self-supervisedly trained end-to-end by using multi-view images. Next, we explain our interreflection-aware illumination module that explicitly models indirect lights, based on reflectance and occlusion in the scene. To start with, we identify direct and indirect lights by shooting rays from a surface point to faraway light sources. If a ray reaches the light sources without any obstruction, we call it a direct light. If the ray is obstructed by an object when reaching the light sources, we call it an indirect light. To estimate an indirect light denoted as LR, we feed the coordinates and normal of the reflectance point x' into an MLP, which outputs a weight denoted as WR. By aggregating all environment lights according to the predicted weights WR, we can estimate the sharpness and amplitude of the indirect light using this equation. The estimated indirect lights can then be integrated into the rendering equation together with the direct lights. However, we observe a special kind of environment light that causes indifferentiability for the rendering equation. We call these lights the tangent lights. As shown in this animation, the tangent lights change abruptly from visible to obstructed at the boundary of an object. As a result, they are not differentiable for the backpropagation process. To integrate these tangent lights into our illumination module differentially, we utilize the Leibniz integral rule. More details about the mathematical formulation can be found in the supplementary document. Next, we show inverse rendering results in comparison with baseline methods. We first compare with phi-SG, a baseline method that does not model indirect lights. Compared to phi-SG, our method produces more realistic and consistent geometry, albedo, and roughness. In this hot dog scene, our method correctly predicts the roughness while phi-SG produces noticeable artifacts for roughness estimation. Similarly, in this balloon scene, phi-SG cannot predict correct roughness, especially for occluded areas such as the back of the top right balloon. On the contrary, by modeling indirect lights, our method can predict reasonable illumination, geometry, albedo, and roughness. Now we show comparison with MII, a baseline method that does not explicitly model indirect lights based on reflectance and occlusion. Compared to MII, our method predicts more accurate albedo and roughness. For example, as shown in the third column, MII does not capture the strips on the top part of the jars. Similarly, in this balloon scene, the second column shows that our method precisely predicts the text on the balloon while MII predicts blurry albedo. Also, MII is sensitive to bright lights, as shown by the bright spots on the roughness image in the third column. We show 2 more qualitative comparisons with MII, where our method predicts more clean and realistic environment map. Thanks to our physics-based inverse rendering model, it can be easily applied to applications such as relighting and material editing. Here we show results of relighting the scene with outdoor or indoor illumination respectively. We also show material editing results where we change the color or roughness of objects in the scene. Our method produces realistic editing, demonstrating its promising performance in disentangling geometry, illumination, and materials. Thanks for watching.